Hello, everyone. Yeah, thanks for coming. I'm Chao Gao from Intel virtualization team, and I'm here to talk a little about some improvements to microcode loading in Zen. So, firstly, why we are doing this work? As you know, in the past almost 2 years, several vulnerabilities are found. For example, L1TF and MDS. They can be exploited to launch side-channel attacks and steal sensitive information from your system. And it may be worse for multi-tenant cases, for example, cloud computing. Some vulnerabilities can be fixed with software mitigation, but some of them are not. So Intel provided microcode update. Yes. Provide microcode update to mitigate such issues in an efficient way. Yes, so because software-only mitigation may introduce significant overhead. For this case, updating your microcode is a must. But for a data center or cloud service providers, it is painful for them to update the microcode because in general you should schedule maintenance events and notify all your customers to ask them to be aware of the maintenance. And so our customer needs an efficient way to update the microcode, just like when they find a bug in the hypervisor or in the OS, they can use some live patching or live replacing the bug in kernel or the bug in hypervisor. So they want to update the microcode in a few seconds. But currently, we can't meet their requirements, so that's why we are doing this work. So let's give some basic concepts of microcode update on Intel platform. Basically, microcode update is an Intel supplied data block. There is low executable binary inside it, and it is always used to correct errata in the processor. And this facility is introduced in P6 family processor, so from then on P6 family and the later processor can load the microcode update. The microcode update is comprised of a descriptive header and unencrypted update data. In the descriptive header, it specifies a list of processor signatures, and it also has a revision number. So before you try to load microcode, you should check the updated reversion in the processor, and to make sure the revision number in the microcode update is lower than the reversion you are using. This is the steps to load a microcode update on one CPU. So first, we should perform a checksum of the given microcode update, and to ensure the update isn't corrupt. Second, we can get targets. We can get current CPU signature with the CPU ID instruction and go through the header and extended signature header in the microcode update to check whether current processor is covered by the update. And then we can read MSR x32 BEL's signature ID to get current updated revision and check whether the microcode update is newer. Then we store the base address of the encrypted data in the microcode update to EDX and EX, and then write MSR x32 BEL's update trigger to trigger the microcode loading. And finally, we read the MSR x32 BEL's signature ID again to check whether loading update succeeds or not. Actually, regarding to loading a microcode update, there are 3 typical ways in terms of when we do the update. So the first method is updating microcode during system initialization. For this method, you should get new BELs from your OEM, and you also can get microcode update from Intel's website. And the new BELs should incorporate the microcode you want to load. Generally, you should shut down your server and flash the microcode to a chip on the motherboard, and then you reboot the server. So this way is considered the most reliable way, because we wouldn't like to trust the BELs would do everything correctly. But in the process, we need a system reboot, so the downtime is long. And the second way is updating microcode during kernel boot up. So this method is also known as early microcode loading. Basically, in this mode, you should specify the microcode you want to load in a kernel option or Zen option. And in this mode, when the kernel boot up, the BSP will load the microcode first, and then wake up all the APs and waiting for completion of microcode updating on all the APs, and then we continue to boot. So for this mode, you also need to reboot your system, so the downtime is also long. The third mode is updated microcode at runtime. This mode is also known as late microcode loading. So in this mode, you can update microcode on your long-running system. You don't need to reboot your server. So the downtime is negligible. But in practice, there are a lot of challenges to do a runtime update. So here is the microcode loading support in Zen. Currently, we support early loading. So to early loading, then suppose microcode loading for both legacy boot and EFI boot. For both of them, you should specify where the ucode is located, and then you can check the output of XLD message to determine whether the processors get updated or not. As to later loading, currently Zen implements on HAPcore, a sub-function of the platform OP, to load a microcode blob, but there's low user space tool maintained in the Zen upstream, and there are several issues in the current implementation. This is Zen's current implementation. At the beginning, a tool in the DOM0 user space would invoke a help call with the blob to be loaded as a parameter. Then we will create tasklet and schedule it on CPU 0. And in the tasklet, CPU 0 pass the blob and loading the shootable microcode it finds in the blob. Then CPU 0 create a tasklet again and schedule it on CPU 1. Then CPU 1 repeats the work done by CPU 0 again and create a tasklet for CPU 2 and on until the next CPU completes its loading. Then we finish the whole microcode loading in the system. So, but we can see several issues in the process. So, first, the CPUs run without any control. For example, if one CPU is updating its microcode, other CPUs in the system can do anything. We don't know can do anything it wants to. And its workload may be very different. And another issue is we pass the same blob many times. Think about you have a high-end server that has hundreds of CPUs, and then you would pass the same macro blob hundreds times, and it involves hundreds of memory allocation and deallocation. So it wastes a lot of time. And the third issue is interrupt would impact the process. So if during the process is loading microcode update, if an interrupt arrives, so it will go to other execution flow. And the next issue is the whole process is processed, serialized. Okay. So it's a summary of challenges of late microcode loading. Firstly, is interactions between workload on CPU and microcode update. So generally, when you try to live patch your system, your hypervisor or your OS, when you try to patch a specific function, so generally you don't want it is being used when you try to update it. So it's the same for updating microcode. So workloads may interact with features to be passed by microcode update. So we shouldn't use it. And the second thing is various changes can be done by microcode update. For example, microcode can change the behavior of existing instruction, and it can introduce software visible features, for example, MSR. And you don't know in the future what the microcode update will change. And some events may interrupt the CPUs. For example, external interrupts and NMI and machine check. They will let your processor go handle other activity, go handle other events, and go to another execution flow. So another challenge is there might be hundreds of CPUs to be updated. So in this case, if you process the loading in your system serialized, then the downtime would increase. And generally, when the interrupt is disabled in the whole processor, so we consider the system would be unstable if interrupt is disabled for a long time. So how to deal with these challenges? This is our proposal. We can rendezvous with CPUs inside the stored machine context. In this rendezvous, at this rendezvous, all CPUs will only do what is necessary and use a small set of instructions which are considered safe to use when updating microcode. We also block NMI handling to avoid CPU get out of control. To machine check, at the net place, only critical machine check would happen. In that case, the system would reboot anyway, so we can't do anything for it. In our proposal, we also try best to minimize the duration of microcode loading. For example, some non-critical process like a parsing blob are done before rendezvous. And to accelerate update on a system with a large number of CPUs, loading microcode is done in parallel. So this is our improved implementation. We also start from a help call from user space tool, and we pass the blob locally and store suitable microcode update. It is only done once, and the other CPUs didn't pass the blob again. Then we rendezvous all CPUs into a stored machine context. In this context, interrupts are disabled, and NMI handling is blocked until all CPU in the system finish the microcode update. Also, loading microcode is done in parallel, and at the rendezvous, CPUs only execute instructions related to microcode update. So, yeah, this is our improvements, and other improvements. Yeah, we also introduced a tool to load the microcode at runtime. It is based on a patch from kernel, and this tool is placed under tools/misc, and the microcode blob should be specified to use this tool, and the hypercore interface remains the same. So it won't bring tools maintained out of tree. We also reduce the complexity of microcode loading a lot. We are not intended to support mixed processor stacking or model, and clean up the per CPU cache, microcode cache, and instead use a global microcode cache. So this is our future work. Currently, we find an issue that microcode reversion in DOM 0 point of view gets stale after data loading. So possible solution is reread updated revisions and enumerate related CPU features in DOM 0 kernel. So currently, my latest V7 didn't fix it. So, any questions? machine. Yeah. I don't get your point.
Then we'll need to rescan CPU ID to find the value by microcode.
Actually, I then doesn't rescan the CPU features after microcode loading. I think it's also another work we should do in the future.
Yeah, and probably require
Yeah, yeah. Yeah. Yeah, that's right.
I think you want to return to the feature, but only to the microcode today.
Yeah, the CPU. Okay, any other questions? Okay. Thanks. On what? On what? Yeah. On the improvement microcode loader in that. Okay, thank you.